Okay. So you also got this guy. I need to. Oops. Sorry. So what you're going to do is learn how to wire this to make the lights go on. You have to learn how to make measurements with these tools. Okay. So that's going to be our goal. It's very easy to make measurements with these things. I mean, when you learn how to use it, it gets pretty easy. So really all you're going to need to use is these wires that you're given in the kit, this guy, and 1 of the 2 meters. And it's pretty easy to make the bulbs go on. You might have to use a screwdriver, a Phillips head screwdriver, to make your electrical connections. So, for example, if I want to make one of the bulbs go on, you all see the light going? You all see the light going on? Hold on a second.
Yeah.
Okay. So you're going to hook up 2 of the bulbs in series, and you're going to hook up the batteries in series or parallel. So you're going to do 2 different combinations. So what you have to do is you're going to film yourself wiring this for all the different steps. You're going to film yourself making the proper measurements of voltage and current. Well, both of these measure voltage and current. All right. So you're gonna have to film yourself doing all this. I'm gonna switch cameras. Let me stand up here. So you're gonna film yourself making the measurements. So what I'm gonna do today is I'm gonna talk about basic idea involving circuits, and I'm gonna talk about how we use these. Okay. And I'll talk about what series and parallel means. All the stuff that I'm talking about here is related to what's in chapter 27 in your textbook. Okay? So, all the stuff that's, I know we're a little bit ahead, but the material in chapter 27 is pretty easy. That's why I'm using this lab to cover it. Very straightforward stuff. And so and there will be a homework assignment associated with it later on, not now. But really the goal is to learn how to use these guys to measure voltage and current and resistance too on this board. So this is really all you need for this lab. Okay, and it's really a skill demonstration. I need to see that you can wire a basic circuit up and make the proper measurements. The reason why we do this lab is because students blow fuses when they make the wrong measurements. So we did provide extra fuses for you. Okay, we did provide extra fuses for you in case you blow fuses. You generally will blow fuses when measuring current. You will not blow fuses when you're measuring voltage. And you get to try really hard to blow a fuse. Measuring voltage. Okay. So what I'm going to do is talk a little bit about circuits. And we'll talk about how to make the measurements. There's 2 documents related to this lab. One is the lab itself, and again, it's really more of a skill demo. And then the other one's called the fatal current, which tells you how much current has to go through your body before it kills you. Now, all our labs are designed so that the current is low in the circuit. So it's going to be pretty hard, well, actually almost impossible, to get hurt in these labs. Okay, so I wouldn't worry too much. I wouldn't worry about safety in these labs. These are all very low voltage experiments that we have in this course. But we still want you to be aware of safety issues not only to yourself, but to your equipment. The equipment is very sensitive, especially when you're measuring current. If you do things improperly, you'll blow a fuse, and that's going to cause delays for you. The instruments that you got come in boxes. The boxes have manuals. You've got to read the manuals. They're not the best manuals, I would say that. And the reason why is because we try to get fairly inexpensive equipment. Okay, and so the manuals aren't written in the U.S., and so the English is not that good. But I mean, it's okay. Okay, the manuals are okay. So, but you need to read through them to help you. To read through the manuals, read through the multimeter lab, and read through the fatal current. I expect you to read those. Okay. Like I said, the currents are not going to be high enough to kill you in any of the labs we do this semester. Okay. So let me talk about electrical circuits. Let me talk about how to build a circuit, what they're made of, and we've talked about electrical potential already. So this should be fairly, this should be a fairly straightforward presentation, I hope. Okay. So I guess the first question to ask is, what causes, just a second here. Let me change screens. What causes charge to flow in a wire? We are going from electrostatics to the case where charge is going to flow in a wire. You want to push electrons through a wire in the same way you want to push water through a pipe. So in order for you to get electrons to move through a wire, you have to have a force on the electrons, which means you have to have electric field, because the force is Q times electric field. So you need an electric field that goes along the wire. We learned on Friday that if you have an electrical potential difference, you have an electric field. If you have a potential gradient within a wire, you have an electric field. And that's going to cause the electrons to move in the wire. And a simple device that does that is a battery. So a battery will produce an electrical potential difference between the ends of the wire. It will also give the electrons a path. The battery is like a water pump. It's going to pump the electrons through the wire. You can think of it again as a device that maintains a delta V, or electrical potential difference, between its positive terminals and its negative terminals. Okay. The delta V tells you that you have an electric field. And so you're going to have a force on the electrons in the wire. By the way, in the wire, it's the electrons that move through it. You can also have electric current in a solution, but if you have an electric current in a solution, they can either be due to ions or electrons. The rate in which charge flows in a circuit is called the electric current. Okay, so let me draw a little picture on the board. So what I've been saying is, if I have a wire, okay, here's my wire, and I want the electrons to move along the wire, what I do is connect a battery. Okay, it's not as simple as this. This is what's called direct short. Okay, but you hook up a battery, so you have a potential difference between the two, and the electrons will move in the wire. Okay. That's how you get them to move. In the previous chapters, everything was static. Now we're in chapter 27, as they're moving. So we want to make the electrons move. So the battery gives the electrons energy. And the rate in which charge flows is called electric current. And it's denoted by the letter I. And here are some examples of electric current. Please stop me if you have any questions during this presentation. Okay, so there's some examples of electric current. Electrons flowing through a wire, a beam of positive or negatively charged particles. There's a current there. It's not described in the same way as the electrons moving through a wire. Or you think the electrolytic solution with charges moving in the solution. I mean, you've probably done that. If you've had chemistry, you've done that. And it turns out that the current to a positive charge moving to the left is exactly the same thing as a current, a negative charge moving to the right. They're indistinguishable. Okay? Plus charge moving to the left is the same thing as minus charge moving to the right. They're indistinguishable. And the reason why is because in a battery, this is plus and this is minus. Whether this gains positive charge, okay, or this loses electrons, no difference. So let me show you a little bit of a brief video. One second.
Suppose that we have two objects, one positively charged and one negatively charged. If positive charge can somehow flow to the negative by moving through a wire, for example, both objects will eventually become neutral. If negative charge flows to the positive, the effect is exactly the same. Both objects become more neutral. Because positive charges moving toward negative charges and negative charges moving toward positive charges have the same electrical effect, we can describe both processes as an electric current flowing from positive to negative. In most real conductors, it is the negative electrons that carry current. But by convention, we consider current as flowing from positive to negative, without regard to which type of charge is actually carrying this current.
And this is an important issue to make sure you understand. There's no difference between the two. They're physically indistinguishable. Even though in reality, it's the electrons that are moving from negative to positive in a circuit. Okay. So there are two types of current that one can talk about in a circuit. One is called conventional current, and the other one's called electron current. So when you're describing what's happening in a circuit, or when you're analyzing the circuit, whether you're talking about positive charge moving to the negative terminal, or electrons moving to the positive terminal of your battery, when the analysis will be correct as long as you apply the laws of physics. So it doesn't matter what kind of flow of charge you use in your analysis. Either case will give you the correct answer. But in reality, it's the electrons flowing through a wire, okay? In fact, I will a lot of times just use conventional flow, because before it was determined that it is the electrons flowing through a wire, physicists always said the positive charge moving from the positive terminal to the negative terminal. But again, if the negative terminal gains positive charge, or the positive terminal gains electrons, the same thing. Okay. So we want to talk about what is the current in a wire. What does this mean? We want to define how much charge moves past the surface that is perpendicular to the motion of charges in a certain period of time. So imagine a wire. We're making the geometry simple. And we have electrons moving to the right with a speed v sub d. In a time delta t, how many electrons move from left to right? Well, let's define the distance L as v sub t delta t, and we'll look at the cross-sectional area A. The volume swept out by the electrons in the time delta t is the cross-sectional area of the pipe, or I'm sorry, not pipe, wire, times v sub d delta t. Area times distance equals volume. That's the volume that's swept out. If we know the number of charge carriers per unit volume, we'll call it N, and we know the value of the charge, then the amount of charge in that volume is N times A times V delta T, and then times Q. Q is the value of the charge. So let me go back and go through this again very quickly. So we have a pipe. I want to know the volume swept out by these electrons as they go from here to here. This distance L times A is volume. But L is the v sub d delta t, velocity of the electrons times time. And then the number of particles in here is the number of particles per unit volume times the volume. And if I multiply by the charges of these particles, Q, then I have the total charge that moved from here to here. If I divide by time, then I get N, V drift, delta T, and A, and Q. I'm sorry, not delta. That's called electric current. That's the number of coulombs per second moving through that wire. The unit is the amp. Coulomb per second. coulomb per second. The amp is actually a fairly large. The amp is a fairly large number. An amp of current represents a lot of electrons. Typically in a circuit, like in a computer, you have milliamps, microamps, nanoamps, depending on what part of the computer you're at. If you're dealing with devices like a refrigerator, then you're dealing with amps of current, like tens of amps. Air conditioner, we're talking about 30, 40 amps. Just look at the fuse, the circuit breaker, and give you an idea how much current is in the air conditioning system. Okay. So we have amps, milliamps, minus 3 amps, microamps, and maybe sometimes you talk about nanoamps. Typically, these are the units to deal with, or amps. If you're working with some heavy appliance. Okay. So instantaneous current, see, what I drew here, what I wrote down here is called the average current. So delta Q or delta T is called average current. Instantaneous current is dq dt. And so that means that if I is dq dt, then delta Q is the integral of I dt. It's a fun question to ask. How many electrons are flowing in a wire if you have 1 amp of current?
Is it 1 mole per second?
No, it's not 1 mole. It's actually less than 1 mole.
Oh.
Yeah, that's a good guess, but yeah, it's less than 1 mole. So let me work this out real quick. Actually, that's actually closer to a million amps, I think. No, 100,000 amps. There's very few devices that run at that kind of current, although they do exist. So 1 amp is 1 coulomb per second. Okay, so let's look at 1 coulomb per second. And an electron is 1.6 times 10 to the minus 19 coulombs. If I divide this by 1.6 times 10 to the minus 19 coulombs per electron, that's going to give me the number of electrons. And if I do this, the coulomb will cancel. I'll get electrons per second. And I'll get 6.3 times 10 to the 18 electrons per second. That's how many electrons are flowing through a wire if you have 1 amp of current. Now these electrons are bouncing off atoms, and so they're dumping their energy into the atom. And what they do is they dump it in the form of heat. So if you have a cable that's running at a fairly high current, like 10 amps, you can probably feel it getting warm. And that's because you have, in the case of 10 amps, you have 6.3 times 10 to the 19th electrons bouncing off atoms per second, transferring their atoms, their energy to the atoms. So when the electrons are moving in the wire, as they bounce off the atoms, they're bouncing off in the atoms at fairly high speeds. Okay. However, if you measure the amount of time it takes for an electron to go through a cable of this length, you'll find that it takes quite a long time. And that V sub D you see in the equation represents the amount of time a single electron it takes to go from here to here. This number is actually pretty small. We're talking centimeters per second. The reason why that number is small is because it takes the electron a long time to get from one end of the wire to another, because they're continuously bouncing off the atoms. Okay. As they bounce off the atom, they're bouncing off at very high speeds. But every time they bounce off the atom, they actually do lose some of their energy. That's why you have to have a battery. The battery always has to be there because the electrons are always losing their energy. Now, if you do an experiment and you measure voltage and current, in this experiment, a person measured current as a function of voltage in a circuit. There are materials for which that graph is a straight line. If you do an experiment and your current versus voltage give you a straight line, we say that that material obeys Ohm's law. Okay. Basically, it says that the current is proportional to the voltage, vice versa. And the proportionality constant is called the resistance. So you will find Ohm's law is delta V is I times R, or I is delta V over R. There are a lot of materials that obey Ohm's law. A light bulb does not. So, for example, the green curve that you see would be more representative of a light bulb. Let me blow this up here. So the green curve is more representative of a light bulb as opposed to a material that obeys Ohm's law. And I'll bring in devices that obeys Ohm's law. In fact, in your kit, you have devices that obey Ohm's law. We're not going to be really looking at Ohm's law. Okay. In this lab, the next lab we will. You get these little things called resistors in little packets. Those are designed to obey Ohm's law, where delta V is proportional to I. Now, if you put too big a voltage on it, you're going to get delta V not being proportional to I, and that means that the material does not obey Ohm's law anymore. Okay. That line should be a straight line, independent of the applied voltage. Then the material obeys Ohm's law. And these are the quantities we're going to need to learn to measure in this lab. Okay, we need to measure voltage, we need to measure current, and we need to measure resistance. So let me tell you a little bit about circuits, just the parts of a circuit. So here's an example of a circuit. That's called a schematic diagram, the picture you see there. The picture shows you the battery. The battery is symbolized by a long vertical line and a short line in that figure. So in this figure, this is the long line, this is the short line. The long line's positive, the short line's negative. They're both vertical. Okay. Of course, if I rotated this by 90 degrees, then if I put the battery along this vertical wire, then I'd have to rotate these two lines by 90 degrees. Okay. Basically, it's a long line and a short line. That's how you signify a battery. The white lines that you see represent the wires. So this is a map for how to wire a circuit. This R is called a resistor, also called a load. And in our lab, our resistor is going to be a bulb. So we will have something that's not ohmic, meaning that if you plot voltage versus current, you're not going to get a straight line, but you can still define the bulb's resistance. It just that it changes as the bulb gets hotter. Now, all batteries or all power supplies have something we model as an internal resistance. In a battery, that internal resistance is really due to the chemistry of the battery. As the battery gets older, the internal resistance gets higher. Eventually, it's so high that it cannot deliver enough current to your load. So if this were a bulb, if this got worse, as the battery got worse and worse, this would get bigger, and it would not be able to make the light go on. And you would say, okay, I got to replace my battery. That's because the internal resistance gets bigger. So they do affect the circuit. If you have a power supply, which you'll see a weird power supply we'll use later on this semester. But if you have the power supply, these are designed so that the internal resistance is very low. Because the object is to not have your internal resistance affect your circuit. The EMF is the voltage that's labeled on your battery. What the load really actually gets, so if you put a voltmeter and measure the voltage across this load, like the light bulb, that's called a terminal voltage. Okay? Oops. Look at that. The voltage that the battery actually gets, the voltage that the bulb gets, or what your load gets, that's called a terminal voltage. It's different from the EMF because of the internal resistance. And this is what's important. What is the terminal voltage that the bulb is getting, or the resistor is getting? Again, in our first lab, the resistors would be a bulb. You might be thinking, what's a resistor used for? Well, the resistor is used to limit current. A resistor can be used to define a voltage that you want. We're going to assume, for simplicity, that the wires have negligible resistance, and that's generally a great approximation. They don't have zero resistance, but they have some. If we were doing the lab on ground, you would actually do an experiment where you'd be measuring the resistance of the wires, but we can't do that here because you need a lot of wires to do the experiment. Any questions so far about the components of a circuit? Okay, so let me continue. This next diagram has two resistors. This broken line like this, squiggly line, that's a symbol for a resistor. It's just one of the circuit elements. If you go around, if you see the orange lines, the orange line form what's called a loop. So this circuit that you see here has three loops. The one defined by the orange line, and then there's one defined by the two resistors, and then there's one that's defined by a battery and the outer resistor. So there's three loops. And we use those loops to analyze the circuit because there's an important principle involved that allows you to analyze the circuit based on what is a loop. A loop is just a closed path for the electrons. Okay, just a closed path for electrons. So you see three closed paths for the electrons in that circuit. This point here, where more than two wires meet, is either called a node or a junction. It's a point where the electrical current can take more than one path. Just imagine you have water flowing in a pipe, and all of a sudden the water hits a T. The water will then take two different paths. So you can always use the analogy with water flowing through a pipe and describing electrical circuits. So the electrons moving through a wire are similar to water flowing through a pipe. Here's a circuit with 3 power supplies, 3 batteries connected, one after the other. Those 3 power supplies are connected in series. If I go back to the previous slide, these 2 resistors are where the positive terminals are connected together and the opposite terminals are connected together. These 2 are wired in parallel. So let me write that on the board. Let me switch views here. So when I wire something, whether it's a power supply or resistors, whatever I have in my circuit, if I have 2 batteries, this is battery 1, battery 2. If I connect them like this, these batteries are in parallel. I'll connect it to a bulb. There are 2 batteries in parallel. Remember, these lines are the wires, so these map out how you're going to wire your circuit. Okay. So I take, this is the negative and the positive, I take the negative of the first battery and connect it to the negative of the second battery. The positive of the first battery connected to the positive of the second battery. They're, basically, you hook them across each other. And so these are connected in parallel. So either one can give energy to the bulb. You can get electrons going from here to the bulb or electrons going from here to the bulb. And since this is that, if this is a battery, if this is 1.5 volts and this is 0 volts, either electrons from either one of these things are going to go through a delta V of 1.5 volts. And as a result, this will be at 1.5 volts. Be 1.5 volts here, 0 volts here. The potential difference across the bulb will be 1.5 volts.
So you add voltage in series, right? And it's constant in parallel?
Correct.
Okay.
Yeah, so if I hook up the batteries like this, like in the figure, with my bulb, now the batteries are in series. If they're all 1.5 volt batteries, and let's say I may define this one to be 0, then this battery is 1.5 volts. The negative of this terminal is connected to the positive of the previous terminal. So that makes this terminal at 1.5 volts. And batteries always maintain a 1.5 volt potential difference, at least the batteries you're using. If this is 1.5, this has to be 3 volts. Well, if this guy's at 3 volts, then the negative of the third battery is also 3 volts. And so this one's going to be at 4.5 volts. Again, there's got to be a 1.5 volt difference between the two. So what happens is the electron, this is like a water pump. Electron comes through, gets pumped to 1.5 volts. Goes through, gets pumped another 1.5 volts. Goes through, it gets pumped by another 1.5 volts every time. So these are like having 3 water pumps in a row. Every time it's giving the electrons kinetic energy. So now you have 4.5 volts here. This end of the wire is connected to this guy, and so we say this volt is at 0 volts. So the bulb has a delta V on electrical potential difference of 4.5 volts. People will call this a voltage, right? I mean, it's always called a voltage, but it's kind of a misnomer. It's really a potential difference. So some people call it a PD, Some people will say that the PV is 4.5 volts. Right? The voltage dropped by 4.5 volts. Notice that when the current's going this way, the potential is dropping. That's because the electric field's that way. Electric field's this way, the electrons move against the electric field. So the potential difference across this bulb is 4.5 volts. The potential difference across this bulb is 1.5 volts. Because in this case, you're not pumping the electrons twice through the battery, or 3 times. Right? Here you're pumping, the electron goes through 3 different pumps. Each time it gains kinetic energy. Just imagine that 3 water pumps in a row. Every time the water goes through the water pump, it's going to gain energy. That's not what's done here. Does that make sense? Now, if I take 2 bulbs and hook them like this, both bulbs, you'll notice in both cases, one side's at 4.5 volts and the other side is at 0 volts. The delta V across both of them is exactly the same. And so we say that these are hooked up in parallel because they're the same voltage, but the same potential difference. They are hooked up across each other. These 2 are hooked up across each other. This is parallel. This is series. So what you're going to do in the lab, and in the demo, is you're going to do a case where you hook up the batteries in series, the bulbs in parallel, and then you're going to switch it. So electrons need a complete path to flow. What's the difference between series and parallel? What's one of the key differences? Suppose the wire gets disconnected here. What happens? Let's say the wire got disconnected right there. What happens? Well, is there still a path for electrons to go through? The answer is yes. So in parallel, if one of them gets disconnected or this battery dies, this battery will still do the work for you. And so the light bulb stays on. But what if one of these batteries dies? Or what if I disconnect this somewhere, like this? What happens? Everything turns off. Do I have a complete path for the electrons? The electrons have to have a complete path. You have to be able to go where they started from. They have to have a closed path. If I break this off, electron goes here, comes here, and then says, okay, where do I go now? I can't do anything, I'm stuck. Okay, or when the electrons go through this branch, they get to this point, they get stuck, they can't go anywhere. So in the case where they're in series, if I break a connection anywhere, or if one of these dies, everything's off. Here, if one of these goes off, the electrons still have a path. Same thing here. If one of these bulbs dies, the electrons can still go through here. Okay? And they're going to be both equally bright if they're identical bulbs because both of them have a delta V of 4.5 volts. And in fact, let me take out this bulb for now and ask the question, in which case is the light bulb going to be brighter?
Well, the one that has a greater potential difference, right?
Yeah, so this one, right? Because the electrons are accelerated 3 times, right? So you have electrons with 3 times the kinetic energy to go through this bulb, so this bulb will be brighter. Even if I do this, Both can be at 4.5 volts. Of course, these batteries will die faster because they're pumping out a lot more electrons. Okay. But even if I do this, both are going to be equally bright as compared to that one. But if I do this, if I put two bulbs in series, now the energy is going to be divided between the two. Because the resistance impedes the flow of charge. It reduces the flow of charge. So now I've essentially doubled my resistance. I reduced the flow of energy. So each one is going to get half the energy. And so my bulb will get dimmer. Well, there are things to look for when you're doing the lab. And by the way, when you do the two bulbs in series, it is possible that the bulbs will not light up at all. But you should be able to measure a voltage across them. If they have a non-zero voltage across them and they're not on, just that they're not getting enough energy. You can always prove that it's working by measuring the voltage. Okay, so we've gone through these. Okay, so I want to stop here. I want to talk now about the circuit. We can talk about this next week some more. So I'll come back to this description of electric current later. How do we measure current? How do we measure voltage? Okay. What's true of any measuring device? If I take a thermometer and I want to measure the temperature of some container, I take the thermometer and I put it in the container. And of course, it reads the temperature. But isn't it true that the thermometer stops changing its temperature, the value on the thermometer stops changing once its temperature matches the temperature of the container it's in? Right? So basically, the thermometer and the material in the container are at the same temperature when you're making that measurement. When you're measuring something with a ruler, the distance along the ruler equals the length of the object. The same thing is true when you're measuring voltage and current. When you're measuring voltage, you have to connect your voltmeter so that the voltage across it is the same as the voltage across the battery or the light bulb. So how do you hook it up? Well, we established the fact that when these two light bulbs are hooked up in parallel, they have the same potential difference across them. So you actually have to hook up the meter in parallel to the battery or the light bulb. You hook it up in parallel, the voltage across, or the potential difference across the meter will be the same as the potential difference across the item you're measuring. These don't have clips, so it's hard for me to demonstrate. But basically, I would put, for the light bulb, I would put one terminal here and one terminal here to make the measurement. That's what it means across. They're in parallel. So my meter now is in parallel to the bulb. And it turns out it doesn't matter whether or not I switch the red and the black. If my direction is wrong, the meter will say negative. Okay. So for measuring voltage, your meter has to be in parallel. Now, I'm trying to video with my camera, so I don't want to switch I don't want to switch views here, but as you look on here, let me use a bigger view. Okay. As you look on this thing, you'll see there's a V over here. And so what you're going to do, you have to move the dial to the V, and there's different scales on here depending on the accuracy you want. The smaller the voltage, the greater the accuracy you can get. So, precision, I mean. So I have it on the 2-volt scale. There's a 2-volt scale, a 20-volt scale, a 200-volt scale, and a 1,000. You're not going to use a 1,000-volt scale. Okay? So you're either going to use a 2 or a 20-volt scale on this one. So right now it's on the 2-volt scale. Right now it's on the 20-volt scale. Okay. All right. For the other meter, right now the other meter is off. I'll put it on the, this is a very insensitive meter because it only has a 200-volt scale and a 600-volt scale. So these are, this little guy is cheap, but it measures high voltages. I measured the battery voltage the other day with this cheap one, and it's way off. And I think it's because the sensitivity is not that great. Okay, that's why I call it cheaper. Okay. I think I'm blocking the view, sorry. Let me do it again. Okay, so right now I have it on the, closer, the 200-volt scale. Okay. And the cheap one only measures direct current. Only DC current. So what we're doing right now is we're talking about DC current, direct current. Measuring voltage is easy. Whether you're doing the I'm going to use the better one. Just give me a second here. Unplug everything, that's it. So I have this on voltage. If I measure the battery voltage, it's going to be tough for me to do. That's why I wrap the wires. And I wrap the wires around like that. One of my batteries. Maybe you can see what the voltage is. I'm not going to do it complex. So this is what my battery voltage is. Of course, when you're sitting down and doing this, it's much easier than me standing up in front of this camera. It's on the opposite side of the room. Okay, so you see that's how I measure the voltage. I just put the leads across the battery, and that's it. I do the same thing for the light bulb. Like I said, measuring voltage is easy. So this should be sufficiently robust, and for now, I don't want you to try it. Do not try what I'm saying here. This is sufficiently robust for me to measure AC current. And my concern here is okay. I can actually take these and stick them into the wall socket and measure the voltage. I wouldn't do it for you right now because you know this, okay, unless you have experience. But I can actually stick these in a wall socket and measure the voltage. You should get around 120. That's how robust it is. In fact, this guy can go up to 700 volts. By the way, these are kind of new to me because the ones we had ordered originally, we couldn't get, so I'm not as familiar with these I mean, I'm fairly familiar with these, but the numbers on the dials are all different on different meters. And this is like about $40. So if you do break one of these, if you want to continue your lab, you might have to go buy it. You might have to go buy a replacement if you break one of these. If the fuse goes bad, you have to replace the fuse. Okay, you're going to have to open this up. You're going to have to take this red thing off and open it up and replace the fuse. Okay, if it goes bad. And replacing the fuse is not that hard. And Tyler will be making videos on this. Questions so far? Now resistance. Resistance tells you how really a measure of opposition to current. And so there's a resistance is basically delta V over R. Resistance, delta V over R. Is volts per amp. Okay. Resistance is just volts per amp. And it's also known as the ohm because it's named after Ohm's Law. And I can measure resistance. In fact, I can measure the resistance of my body. So on this guy, you'll see a symbol that looks like this. That's a symbol for the ohm. And you'll see a orange scale. Okay, you'll see an orange scale on here. What I'm going to do is I'm going to measure resistance. I'm going to be measuring the resistance between two fingers. And it's in the millions of ohms. That's megohms. Okay. If you put the two prongs closer together, you'll get a lower resistance because you measure the resistance across two parts of your skin. So if you do this, you can measure the resistance between those 2 points on your body. And let's see, what do I get? I'm not grabbing it very well. Let me just do it between my two fingers. And I'm just going to touch point. So I get about 1 million ohms just by holding it like this. I get about 1 million ohms. If you do it a ball by itself, it's tough to do. You get like a couple ohms. Okay. Again, when you're measuring resistance, you got to take the device out of the circuit. Do not measure resistance in the circuit. Do not have the power supply connected to the element, like a light bulb or a resistor, to measure resistance because you'll blow the fuse. So what is it doing? It actually runs a current through, well, right now it's running a current through me. I really don't feel it because it's a small current. I would start feeling it once I get to 10 milliamps. Once I get to 50 milliamps, my muscle contracts. And then I can't let go. If 100 milliamps goes through me, I'm dead. Okay, 100 milliamps will kill you. When you get way higher, you get to an amp, you actually might not die. But something else happens. You start cooking. Okay. Yes, tasers are at high voltage. Tasers are in the thousands of volts, and they're low current. Okay, and as long as you don't have a high current going through your body, you're going to be okay. But if you get 50 milliamps through your body, you will feel it and your muscles contract. You'll feel it at 10 milliamps. When you get to 100 milliamps, even 75, your heart will start going into fibrillation. Your heart rhythm will get out of whack. Eventually what you're getting is a heart attack. and you die at 100 milliamps. But at 1 amp and above, that doesn't happen. It doesn't mess up your heart. But what happens is you start cooking. So I'm going to try to, I won't do the demo, I think I'll have a video. I'm going to try to make a video of running a current through a hot dog later on this semester. It shows you what happens to the body when you run the lamp through it. Okay. Well, there's a lot of charge in a lightning strike. Yeah, but you're right. They'll burn, right? The people who get struck by a bolt of lightning, you get a large current going through them, but they get severe burns. It doesn't stop their heart. So they probably have a better chance of survival from a lightning strike, although they get severely injured, as opposed to getting 100 milliamps through their body. But you still get burned. You do get burned. Okay, so far I've talked about voltage and resistance. Again, to measure resistance, again, in parallel, but it's got to be out of the circuit. The hardest one to measure, by far, is current. Remember that to measure current, the amount of current that goes through the bulb has to be the same as the amount of current that goes through the meter. If I put it in parallel, then the current reaches this point and it splits two different directions. Hold on, let me turn this off. So if I do this at the ammeter, that's not too bright. Okay, if I do this A for an ammeter, what happens is the electrons go here and then take two paths. And that measurement is not going to be indicative of what's going through here. I want to get the same amount of current. So imagine you're measuring, think about measuring water flowing through a pipe. How are you going to get the same amount of water through this guy and this guy? Well, you got to put it right next to it. You actually have to break your circuit and put the ammeter into your circuit. It's got to become part of the circuit. So then the amount of, if you're thinking of water, the amount of water that goes through here goes through here. The amount of electrons that go through here go through here. So you got to hook them up in series. But there's more to it than that. And I'm going to be going over in time, but there's more to it than that. These things are sensitive. It's actually not easy to measure current. You have to be on the right current scale. Because it does use a resistor to measure current. So on here, there's 3 current scales. 20 milliamps max, 200 milliamp max, and 10 amp max. So these two guys here are used to measure the current. So I forgot to tell you about these guys. So when you make the measurement, one is always in the common, and the other one is the one that you move. For voltage, you put it here. For current, you put it on either one of these two. If you're going to be measuring something less than 200 milliamps, you put it up here. For 10 amps, you put it. Oops, sorry. I'll do it again because that was in the picture. Here's the negative side. This is for voltage. This is for current, below 200 milliamps. This is above 200 milliamps. If you measure something that's like an amp, and you hook it up like this, you will blow the fuse. Okay? If you hook it up like this, and you have it on the 200, you have it on a 20 milliamp scale, and you measure 100 milliamps, you might blow the fuse. Okay? The problem is what makes it hard is that it's very easy to blow the fuse. So number one, you have to be in series to measure current. Number two, you have to be in the right scale. So when you do the measurement for this, okay, so pay attention very carefully. When you do the measurement for current for the bulb, you are going to measure the resistance of the bulb. You're going to take your voltage over the resistance to get the estimated current. Okay, so estimate the current. And from that value, you pick the scale you're going to use. Now, suppose my prediction, because a bulb is not really obey Ohm's law. Suppose my prediction assumes I'm going to measure half an amp. So I put it on this scale like this, okay? But instead, I measure 50 milliamps, which is a small current. Then what do? Well, this is what I do. I disconnect this from the circuit, or actually, yeah, I disconnect it from a circuit. I switch from here to here, and then I turn to the right scale. Okay. Be careful when this is connected to the circuit and you do this, you can blow the fuse. Change the scale when this is disconnected from the circuit. All you got to do is remove one side. You remove one side, that's it. Okay. Now it's going to be hard to put this in series because these are the clips on it. I apologize for that. Okay. So all you got to do is disconnect from the circuit, make your changes, and then make the connection. Because if you blindly go like this, while it's in the circuit, you might blow the fuse. My goal is to minimize the number of fuses we blow. I did have one semester where the entire class didn't blow a fuse. That was awesome. That was very great. And it was really hard. We all make mistakes. I blow fuses too. Okay. So this is going to be the hardest thing to do is measure current. And you need to practice. So one of the things you got to do is practice wiring this up. So you're practicing wiring this up, and then you're practicing making the measurements. And when you're ready, you make the video of yourself going through all the measurements. That's your lab. Okay? There's no lab report still. Okay? There's no lab report. You're just going to do a video showing me that you can go through all the steps in the multimeter quiz. That's your entire lab report. And if you can do that, no problem, it's a 20 out of 20. Because it's a skill demonstration. Because the next labs, you're going to be using this to build circuits and make the necessary measurements. Okay. So this is an extremely important lab because you have to learn this skill. And you have to demonstrate to me that you know how to use the multimeter. Now, some of you folks have played around with these before. And so you should have no problem making the measurements and setting these up. Okay, this should be, if you've played around with these things before in high school or whatever, or even at Sierra in the mechatronics class, you're not going to have any problem with this. This is not designed to be hard. This is designed just to make sure you know how to use the multimeter. Like I said, the hardest one is to measure current. Voltage is easy, resistance is easy. Well, one thing that's going to be hard, we've never done this before, is doing this online. And it just scares the heck out of me doing this online, but we'll see how it goes. Okay. Questions? So next week, I'm going to take your questions on that, and then I did have a question on the, I'm sorry I went over. I did have a question on the Gauss's Law worksheet. So let me, if you want to leave the meeting, go for it. I'm done, but I know I have a person who wanted me to do the Gauss's Law problem. Okay, so I'm going to do it right now. So the Gauss's law problem is just part A. We have a charge distribution that looks like this. Basically, if I plotted that, looks like this. So I have a slab. Here's the origin. This is b over 2. This is minus b over 2. And now I'm going to use Gauss's law. This is a slab. It's the same thing as the a plane in a sense. So I'm going to use a pillbox. It'll be a little bit longer. A pillbox that's a little bit bigger than the thickness of the slab. So you know, since this is positive, the electric field is going to point like to the left on the left-hand side of my Gaussian surface, and to the right, it's going to point to the right on the right-hand side of the Gaussian surface. And so I'm going to have on either side, when I do the integral of E dot N dA, I'm going to have E times A on the left-hand side, and E times A on the right-hand side. Because remember, E and N are parallel on both sides. And this is going to be equal to Q enclosed over epsilon naught. And so I'm going to get 2EA but to find the amount of charge enclosed, I need to find the amount of charge enclosed in this volume. So I need Q enclosed is going to be the integral of rho dV. So my dV is going to be different because it's going to be the area coming out.
What's the n vector?
I'm sorry?
Or the in the first, or the integral E dot, what's is that n?
The n is the normal to the surface.
Okay, okay.
Right, because it's true that the n and the E are parallel here, right?
Yeah.
And so are they here. So they're both going to be E times A. Because E is uniform. So this is going to be the integral of rho times A dx. I think this is the x direction. That's my elemental volume. Because my density doesn't vary in this direction, it only varies this direction. So I'm only going to with respect to x. And so, I'm sorry?
Sorry, I coughed.
Oh, okay. Too many A's. But I call this an A or a B? I forget. I'm going to call it a B because too many A's. Let me just call it a B. And this integral is not that hard. It's the same thing. This integral is the same thing as if I did this. Isn't that true? I'm going to put that too. Isn't that true? And then the 2's cancel. And then the A's cancel. And so my E is going to be the integral. I want to do the math right. And so for x greater than or equal to b over 2, the electric field is going to be, just check my math, okay? And for x less than or equal to minus b over 2, because it points to the left, that make sense?
Oh, okay. So it's just plus and minus in each direction up to.
Yeah, because I'm putting the sign there because it points to the left, right? Using Gauss's law only allows me to find the magnitude, but the direction I can put in from my physical knowledge of what's going on.
Okay.
So there is I made a new document because one of you folks caught a mistake. On the last part, there's four domains, right? My domain consists of 2 different parts here, but on the last part, there's 4 of them. But what I did was I changed the charge distribution from last semester to a new value. I forgot to change the number of domains in part A, I think part H or I. So there's a newer document on Canvas with that change. Are you okay with that then?
Yeah, that makes sense now. Okay, so I see what I'm doing now. So that's good. I should be able to get this done.
So when you do inside the slab, then you're going to integrate from, these are going to be very, you're going to minus.
They're easy integrals.
The same idea as when we did the sphere, except the geometry is different. Okay, so I
do have a question. Sorry.
Go ahead.
On part B, it says it's a Gaussian surface centered at x equals 0 with its left face at negative d over 2 to x to 0. So are they basically saying the left face is half of the cylindrical surface?
Yeah, I'm sorry, I don't have it with me.
Oh, okay.
But there's one right here.
Yeah, it's basically saying that one face is one half of the side and the other face is the other half.
Yeah, so the electric field is 0 here, right?
Okay, and then there's an integral from 0 to. Okay, that makes sense.
Yeah.
Because there's more charge enclosed as you increase from.
Yeah.
Okay.
There's no charge there, right?
Yeah.
Because that's 0.
That makes sense. Okay. Oh yeah, so these are pretty easy questions just for like conceptual understanding.
Yeah, I don't think they're easy. I mean, they're easy once you understand the idea.
Well, yeah, that's the point,
Right.
is to understand it.
But really, they're not. It's not an easy thing. But it's like, oh, and after you learn, it's like, oh, why did I have such a hard time understanding it? That's how this topic is.
Okay.
Professor, so for like the integral, it wouldn't be x squared over 2, and then it would be like d squared over 8.
Did I make a mistake on my integral? Oh yeah, you're right. D squared over 8. I screwed up. Yeah, I was saying check my algebra. Sorry. Yeah,
Okay.
my algebra, my math. Yeah, I really screwed that up.
Thank you.
Okay, sorry about that. Yeah, that's better. Okay. I was trying to go, I went too fast. Other questions? I need to know how the properties of chart lab work, and I need to know how this next lab works. I mean, like I said, this is the first time we're doing this online stuff, so.
First lab's due this Sunday, right?
Yes, but I need to know how that goes. By the way, if you can actually put the video on YouTube, it would actually be better.
We should YouTube and not upload.
If you can upload your file on YouTube and give me the link, that's better than me downloading all the videos. Because I know this will be a longer video.
Okay.
Okay.
We can embed it in a. Oh, I guess when you submit it, you can't.
Well, there's a Canvas Studio. You can actually film it within Canvas Studio.
Because I know when you make a discussion board post, you can embed a video, and then you can just watch it right in the discussion, but it's a submission, not a discussion. So.
I mean, if the only way we could do it in discussion, I'll have you. What I'm trying to do is avoid, make it so other people don't watch it, and because some people are not going to be comfortable with other people watching it.
Yeah, that's. Yeah.
So, but I think you can do it within, and I haven't had a chance. I'm going to try to play around with it and with the assignment and see if we can embed it straight with Canvas Studio. Because some people did. Some of the were embedded.
Sorry.
which is nice.
I have a question for the lab actually. If there's something like I tried doing the sugar and salt and it didn't really work, and also actually the same with the glass rod charge, it didn't really move the water. Like I even used like a really thin stream and it still didn't move it.
The silk
So-
didn't really do a good job.
Yeah. So if it doesn't work, should we just explain what it's supposed to do?
Yeah, that's fine.
Okay.
So one of the issues we see when we're on ground, right? When we're in the lab, I can make it work, but
Yeah.
I don't have that ability because I can swap out something right away and say, "Here, try this."
The charge, I don't know, something about the glass rod doesn't make it seem to hold a charge very well.
It doesn't work as well as the PVC.
Yeah, the PVC is a lot better.
Yeah.
I noticed.
What was that?
I had the same problem with the glass. I could get the PVC charged just fine.
And that's fine. If you can just get that to work, that's fine. I mean, the problem is that the difference. So when you're using PVC, the difference between how the fur likes giving off its electrons and PVC likes picking it up is huge, right? But for glass, it's hard to find things that have the same big difference in the triboelectric series, and so glass is harder to charge.
And you charge it with a silk, right?
You can do it with silk, but ideally you'd like to have something like a material like PVC to charge it with, right? Like a cloth. But you can't have a PVC cloth. There's no such thing.
Yeah.
Something that's really negative. That's easy to. It's very malleable in your hands. You can. That's the problem. If there was such thing as a PVC cloth, we'd use that to charge the glass. That would look awesome. Yeah, the glass doesn't always work very well. So you do what you can. And then just say what the glass would do. It should do, okay? And those
They
are
actually, apparently they make a PVC coated polyester.
what they do?
Yeah, it's $6.20 a yard. That's what it looks like.
It's something that's for us to think about in the future.
Hmm.
Hey, like I said, doing
Interesting.
these online is hard. If you guys were in the lab, we can figure out a way to get around those things. But yeah, if it doesn't work, just say what should have happened. Okay?
Okay, yeah. I'll do that.
So I think I'm going to end it here. You guys are okay?
Yep.
Okay. I'll end it here, so I'll see you all on Friday. And
Homework's due Thursday, right, for lecture, or the main chapter?
I'm sorry, the homework?
Homework's due Thursday,
No, I
right?
thought I changed it. I think I added a couple of days because I didn't finish everything
Oh,
yet.
because the worksheet's due Wednesday. I know that.
Yeah, and the worksheet, we've done all that. We've covered all that material.
Yeah, we've covered them too.
But I haven't covered all material in chapter 25 yet, so I extended the homework to like Saturday or Sunday or something like that. I think it was Sunday.
Awesome.
Yeah. Okay, we'll see you on Friday then.
All right, see ya.
Okay.